So, sorry for the delay. No, let's start. So, I'm talking about drama, concretely about the biggest drama there ever is, about the story of Romeo and Juliet. These are two tenants in a multi-CPU cloud server, and they would secretly like to talk to each other across the CPUs, but the hypervisors tries to prevent it by assigning them to different physical CPUs, so they don't share a cache, and cache attacks are not directly possible. This already brings me to the concrete setting we evaluate in our work. We consider multi-CPU, multi-socket systems. On such systems, you typically have multiple tenants which are co-located on this one system, and they are isolated by using separate VMs. These tenants can then run on different physical CPUs, either just by coincidence or they were assigned by the hypervisor to dedicated CPUs so that cache attacks are not possible. Anyway, we cannot assume that there is a shared CPU cache. Also, we assume that there is no shared memory in the form of, for instance, cross-VM memory deduplication. This is often also disabled for security reasons, and for instance, we saw yesterday that disabling that might be a good idea. Previously, in this scenario, we only had a slow covered channel with a transmission rate of less than 1 kilobit per second, and also no side channel attack. We changed that by presenting our cross-CPU attacks. We exploit DRAM addressing and hence the nice abbreviation DRAMA. We present a fast cover channel that allows transmission rates of up to 2 megabits per second, and also the first side channel attack in this cross-CPU scenario. We exploit reverse-engineered DRAM addressing functions. We do that by having two approaches. And apart from enabling these two attacks above, these reverse-engineered functions also allow us to improve upon existing attacks, namely the Rowhammer attack. Before I can talk about the attacks specifically, I'll have to discuss a little bit DRAM and its organization. DRAM is organized into a hierarchy, or tree if you want to. In modern multi-CPU, multi-socket systems, you have that each CPU has a dedicated memory controller and attached memory. So you have multiple nodes. The memory is still organized into a single address space, and requests to the other CPU's memory is done over the CPU interconnect, for instance, Intel's QPI. Now, if we go one level down, we have, for each memory controller, we can have multiple channels. These are independent electrical links, and for each channel we can house multiple memory modules or DIMMs. Now, for each DIMM we can have multiple ranks, usually 1 or 2, and this often corresponds to the front and back side physically of the module, but not necessarily. And then for each bank can house multiple banks. The typical number of banks depends on the technology you use. On DDR3, you usually have 8 banks per rank. On DDR4, you have 16. Now, finally, at the level of the banks, we have the actual memory arrays, which are organized into rows of columns. But then, each bank also has another component, namely the so-called row buffer. As the name implies, this component buffers one entire row. The typical row size in DRAM is 8 kilobytes. And if you look at this row buffer from a high-level perspective, it has behavior kind of similar to a cache. Namely, there's always one row that is currently buffered or active in the row buffer. And if you have a memory request that targets this specific, the currently active row, then the request is served directly from the row buffer and the memory access is fast. We call such an event a row hit. If a different row is open, then we first need to close the other row that is not targeted, open the other row. So this is, of course, takes time, is slow, and we call such an event a row conflict. On this graph, you can see the access times of potential cache hits, row hits, and row conflicts. And in the green shaded area, you can see that for row hits, we have a minimum access time of 180 cycles, whereas for row conflicts, we take at least 228 cycles, so they're definitely slower. So row buffer behaves like a cache. Well, then let's exploit it like a cache. Well, first we need to find out how physically addresses map to DRAM channels, ranks, and banks. Because only if two addresses are in the same bank, then they have also a shared row buffer. Thus, we need to reverse engineer the DRAM addressing. Now, the mapping to channels, ranks, and banks is done using a subset of physically addressed bits. These bits are often not used directly, but instead first combined into some sort of complex addressing functions. This is done so to distribute the memory traffic to channels and banks more evenly, and thus to increase the performance by using the inbuilt channel and bank parallelism more efficiently. However, these addressing functions are, at least in the case of Intel, undisclosed, thus the need for reverse engineering. We now give two approaches that achieve this, both of which use the presumption that the addressing functions are linear. In other words, they're just XORs of physically addressed bits. For all our tested systems, this was the case, but our analysis can also be adapted to the nonlinear setting. Now, the first approach we used is a physical probing of the memory bus. This picture on the right, this white strip, is the DRAM slot, so where you insert your memory module, and there the pins are actually exposed, so you can easily contact them. So we performed a probing of all the control signals which were of interest for our analysis, so mainly the chip select and dedicated bank address pins. We measured the voltage at the pin with an oscilloscope and can thus recover the logic value sent over the bus. To make this measurement easy, we pick a single address and perform repeated access to the single address until we have found the logic value. So we don't need to perform a full DDR protocol analysis, and we don't need to locate single memory accesses, because that would be a bit more complex than just using one probe. After having done this for enough addresses and all the interesting pins, we feed the results to a function reconstruction, which is just linear algebra over bits, solving a linear system of equations. Now, the second approach we have is a fully automated software-based method. It exploits timing differences coming from the row buffer. These are the same timing differences we have for the attack then later on. It proceeds in two phases. First, in a measuring phase, we try to build sets of addresses that map to the same bank but a different row. We do that by picking address pairs and then performing an alternating access between those two addresses, and also keep measuring the average access time. Now, if these two addresses are in the same bank but a different row, then we trigger a row conflict for each and every access. Thus, the average access time is high. This corresponds to the small peak on the right of this histogram. If the addresses are either in the same bank and same row, which is kind of unlikely, or in a different bank altogether, which is by far the most likely case, then access is fast. This is the large peak on the left of this histogram. We then feed the sets into the reconstruction phase, where we perform an exhaustive search over linear functions with up to n set coefficients. And I know the term exhaustive search always sounds a bit scary, but actually the search space is already so small that this is still very efficient. The total runtime for this reverse engineering, of course, depends on the machine, but in most cases we're done in a couple of seconds. And there we have that the majority of time is still used for measuring, not reconstruction. We analyzed a large set of machines using the, first this one, yeah. When we compare these two approaches, for the probing, we can recover the functions and their labels. So we know, okay, this function computes a channel bit, this function computes a rank bit, and so on. We can't do that for the software-based attack, but in the context of our attack, we don't actually need the labels. Just knowing the functions is enough. For the probing allowed us to find a ground truth, because we are very certain if we do the probing, then we know that these found functions are correct. So we use that then to cross-verify the software-based method, and it also helped us to build the software-based method in the first place. For the probing, of course, you need equipment, a scope, and access to the internals of the tested machine. Here, however, bear in mind that once you have reverse engineered one machine, then you can attack any similar machine as well. You don't need to reverse engineer every single machine you attack. This would be kind of pointless with the probing anyway. The software-based approach, on the other hand, is fully automated, can run remotely, sandboxed, and even on mobile devices, where probing gets a bit difficult due to soldered-on memory. Now, we analyzed a large set of machines using these two approaches, and now give at least a little excerpt of our results. Here you have the mapping of an Intel Haswell desktop system using DDR3 dual-channel memory. Channel is computed by XORing 7 bits together, and bank and rank addressing is done by XORing bits 14 to 17 with the lowest bits of the row index, which starts at bits 18. Now, for a dual CPU server system, this mapping gets a bit more complex, and you can maybe guess that attacking a machine without knowledge of this mapping and just by guessing addresses might gonna get a bit difficult. Also, apparently Intel got a bit lazy with their channel addressing because they just use each other bit. On the other side of the spectrum, we have mobile devices. Here, for instance, a Galaxy S6, where the mappings are usually much simpler. So now let's use these mappings in our cross-CPU attacks. And of course, I'll also have to continue the story of Romeo and Juliet. Our first attack is a high-speed covered channel that allows these two guys to talk across CPUs and VMs. This covered channel works as follows. First, the sender and the receiver, so Romeo and Juliet, need to agree on one bank, which they use for transmission. Then they need to allocate memory, which is in different rows, but in this one bank. This is actually fairly easy to do. Then for the attack, for the actual transmission, Juliet, the receiver, just keeps accessing one of her rows and measuring the average access time. Now, if Romeo wants to send a 1, he continuously accesses his row. This, of course, activates his row in the row buffer. Then, if Juliet accesses her row again, she triggers a row conflict. The access time is high, thus she can infer, okay, a 1 was sent. If, on the other hand, Romeo wants to send a 0, he just doesn't do anything. Juliet's next access is served directly from the row buffer, and this is, of course, fast. We implemented a proof of concept of this covered channel. There we used some tricks, mainly that each bank can be used as a separate transmission channel. We use up to 8 banks in parallel, so transmit 1 byte per time frame, and we also use multithreading to regain some of the channel parallelism which we lose by doing the measuring. On the right, you can see a performance curve for a desktop system, Intel Haswell. So in this case, we're cross-core but not cross-CPU. And we show the bit error probability as a function of the raw bit rate and also the channel capacity. And this channel capacity peaks at about 2.1 megabits per second. For the cross-CPU scenario on a dual CPU server, we still achieve 1.2 megabit per second. And these numbers fare quite well when we compare them to previously proposed covered channels. When compared to the cache-based attacks, which are in the middle part of this section, you can see that our attack is about as fast as cache-based covered channel, and it is also faster than the one using prime and probe, which is the only one that does not require shared memory. So our attacks are not restricted to just the multi-CPU setting. They can also be a threat in the single CPU scenario. Now, there have been previous works targeting cross-CPU covered channels, but the achieved transmission rates are orders of magnitude lower than what you can achieve using the DRAM functions. Unfortunately for Romeo and Juliet, their feuding families found out about their little secret about the row buffer, and now use also the row buffer to perform a low-noise side channel attack so that they can spy on each other. Our attack allows to spy on memory accesses. It works as follows. First, the victim and the spy needs to allocate memory which is in the same row as a memory owned by the victim. Now, as the typical DRAM row size is 8 kilobytes and pages are 4 kilobytes, you have at least 2 pages per row. Due to the complex addressing functions, you typically have even more more than 2 page chunks per row. Here, I also have to say that, please, this is not shared memory. They're just adjacent to each other. They can't access each other's memory. Now, for the actual spying, the first step is that the spy activates a conflict row, which is just any row that is not shared with the victim. Then the spy waits for the victim to compute and in this time possibly access the contents of the shared row. Then in the final step, the spy also accesses the shared row and measures the access time. Now, if this access time is below a certain threshold, then we know, okay, this memory request must have been served directly from the row buffer. And this can only happen if the row was previously activated, so we know that the victim accessed this single address, because otherwise we wouldn't have a row hit. Here you can see this attack, a real application of this attacks. We spy on keystrokes in the Firefox address bar and just keep monitoring the access time to one vulnerable address. And you can clearly see that each time the user presses a button in the address bar, the access time to the vulnerable address goes down dramatically, so we can detect keystrokes. This attack achieves a very high spatial accuracy down to, the spatial accuracy depends on the actual mapping we have in the machines, but we can get down to 512 bytes, which is almost in the range of the best cache attacks. Also, we have a very low number of false positives. This is actually the low noise part of the low noise side channel attack. This allows us to monitor single events, single keystrokes, single memory accesses. This sets it apart from other cache-based attacks, for instance, prime and probe, which has a much more noise and doesn't really allow to monitor single events. One challenge I haven't talked about yet is, well, how to find vulnerable addresses. We do that by using cache methods from cache template attacks. So we perform an automatic location of vulnerable addresses by first allocating a large fraction of the physical memory, ideally in 4 kilobyte pages, and then scanning over all this memory automatically and trying to find vulnerable addresses. So when you propose a new attack, you'll also have to think about, well, what can we actually do against that? Well, the first intuition, well, just restrict the CPU instructions RDTSC and CLFlush. First is used for getting accurate timestamps, the second one for flushing the cache. And while these probably make the attacks harder, they do not fully prevent that. There are alternatives to using these instructions, and actually we already have a cover channel implementation that does not need these 2 instructions. One way to definitely shut down this side channel is, at least in the multi-CPU setting, multi-socket setting, to not also assign the tenants to dedicated physical CPUs, but then to also restrict access to the CPU local memory. Thus, then they never share a row buffer and our attacks are not possible. But then you kind of essentially degrade a multi-CPU system and multiple single CPU system, which kind of defeats the point of having such an expensive multi-CPU system in the first place. So prevention might be difficult, but we might be able to detect these attacks due to the high number of cache misses and row conflicts we induce. Apart from enabling these 2 previous attacks, the cover channel and the side channel attack, we can also improve upon existing attacks, namely the Rowhammer bug. For those of you who haven't been in yesterday's sessions, Rowhammer is about inducing bit flips in DRAM by quickly switching between 2 rows, quickly activating rows. Here you need, for doing that, you need addresses that map to the same bank and to rows which ideally close to each other. And of course, finding such addresses is of course a lot easier if you have the addressing functions. By just guessing it, you might never find these addresses. And in fact, by using our addressing functions, we were the first to document bit flips in DDR4 memory. And strangely, we also found bit flips in system where the target row refresh Rowhammer countermeasures should have been active. So these findings are in a bit of a contradiction to claims that have been floating around the internet that, yeah, Rowhammer is a thing of the past for DDR4. Well, obviously not. So this brings me then to the end of Romeo and Juliet, but also coincidentally that of our presentation. As a final note, the source code for the reverse engineering tool and the side channel attack is available online, so you can download it now. You just have to set a few parameters and press start. You can reverse engineer the mapping on your own laptop. Okay, so then that's it. Thank you for your attention.
So we have quite a bit of time for questions. Okay, I have one. So you already answered one of the questions I had, was, which was, of course, what could be done to, prevent this kind of scary attack. And so, thanks for that. I guess one thing that I'm interested in is, of course, doing this probing takes a lot of work. And so you showed some of the mappings that you were able to recover, but could you give us an idea of how many you actually found?
Excuse me?
Of these mappings where you were doing the probing of different sources of memory?
For the probing, we did mainly 2 machines, a dual CPU desktop and a dual CPU server and a desktop machine in different memory configurations. And we then did a lot of other machines using the software-based approach, including mobile devices, for instance.
So can you quantify a lot? Can you quantify a lot for the software-based approach? How many software-based how many systems did you apply the software-based approach to?
We give the entire list in the paper. I think it was 10 to 15 systems or something like that.
Okay. You mentioned that, oh, sorry.
So did you do any measurements that said basically how close together 2 rows have to be before you can flip bits in them? So if I'm willing to give up like, I don't know, 80% of my RAM, can I prevent Rowhammer by making sure that things only get mapped to rows that are far enough away?
What I was talking about is you need to have a row that is adjacent, ideally to the row that you attack, and ideally you have the 2 adjacent rows to the attacked row, so the row above and the row below.
Okay, so if I get them 3
efficient.
away, maybe I'm safe. If I'm 3 away, maybe I'm safe now.
Yeah.
Okay.
So fascinating work, both this and the one before. Really, congratulations. I have a question about the figure you showed about the physical probing.
Yeah.
I'm actually quite surprised that you took a standard passive probe and touched 3 gigahertz bus and actually managed to measure something and not destroy the system. So if you could comment.
Yeah, that was also my reaction.
Yeah. So
yeah, but it works. Yeah, using such a standard passive probe, you might not be able to do a full protocol analysis because it's too slow. But for the reverse engineering, this was more than enough. So we could easily read off.
So you just took the standard probe and touched the DDR4 bus. And okay. I might save a couple of dollars next time I buy a scope. Okay, thank you very much.
So I'm also curious, what can you describe the experimental setup that you performed all of this in? Was this like in the cloud, or was this kind of a laboratory system?
No, we did it locally.
Okay, so have you tried doing it?
We had local desktop machines, and also we had our own server.
Have you tried doing this in the cloud?
We have not yet, no.
Do you think that kind of the added noise you might see would bring down the transmission rates?
Yeah, definitely, because we tested this on silent systems where there was no other main processing doing a lot of memory intensive work. So of course then the transmission rates will go down, yeah.
But it would be very interesting to see how well it translates.
Yeah.
Okay, let's thank the speaker again.